Welcome to the video lecture on powers of trig functions. In this section, we learn how to integrate various powers and combinations of the trigonometric function. Always check for existing u-du relationships first, like a u substitution. If there's no apparent u-du relation, think about how you might create one. Sometimes we'll choose part of the integrand as the du first, and then see if the appropriate u is also present. It's also often helpful to use some of your unit circle identities. These first three here are going to be used quite often. These are your Pythagorean identities. And then these two over here are what we call our half angle identities, and we'll typically use those when we have even powers of sines and cosines. So be on the lookout for those and have these 5 identities memorized. So our first example is the integral of sine cubed of x, and this is an odd power of sine. So the trick here, or the strategy here, is whenever you have odd powers of sine or cosine, you're going to save one of them to be part of your du, and we're going to convert the others using Pythagorean identities. So, for example, I'm going to take this sine cubed and I'm going to break it up into a sine squared x times a sine x dx. This sine on the end is going to become part of my du eventually. This sine squared x I'm going to convert into cosines using my Pythagorean identity up here. So if sine squared x plus cosine squared x equals to 1, then that means sine squared x is 1 minus cosine squared x. So this is what I've turned my integral into so far. I converted 2 of my sines to cosines, and I saved one of the sines on the side. Now if we break up this integral into 2 different integrals, 1 times sine x dx is just sine x dx, minus the integral of cosine squared x times sine x dx. Now the integral of sine x dx, we know what that is. What's the antiderivative of sine of x? Well, that's negative cosine x. You do need that negative in there. To integrate cosine squared x sine x dx, think of this as a power using our pattern recognition, if you will. I'm going to change that cosine squared to cosine x quantity squared, if that helps you to visualize this. This square is our outer power. This is our g, our inner function. The derivative of cosine wants to be a minus sine of x. Well, that's why we saved that sine of x, because that's going to be part of our g prime. It's missing the negative, so I counterbalance out front with a negative, which makes this sign become a positive. So now we have the correct f prime, g, and g prime that we need for pattern recognition. When you have all the right pieces, the only piece that you actually integrate is that outer power. And the integral of a square is a cube over 3. The plus out front stays put, and what's inside stays put. So here is our final answer, and I can put on my plus c, and we did it. Okay, so for odd powers of sines or cosines, save one of them and then convert the rest of those even powers using your Pythagorean identities. Let's try the integral of cosine squared 2x dx. Now this time it's an even power. When you have an even power of sines or cosines, then that's when you're going to use these half angle identities up here. And we have a cosine, so we're going to use this one right here. Notice what happens when you use these half angle identities. You're going to be given the left side, so when you convert it, look at what happens to the angle. You actually double it. So if this starts as an x, it turns into a 2x once we apply this half angle identity. So since we're starting with a 2x, when we double that, it's going to turn into a cosine of 4x. But the good news is the square is gone. We lose the square when we apply this half angle identity. So here's what this is going to turn into. You're going to get that 1/2, which I'm just going to pull out front of my integral. And then notice the identity again is 1/2, 1 plus cosine of double this original angle. So if you have cosine squared of 2x, that's going to become cosine of 4x. You always double the original angle, but you lose the square, and that's what we want to happen. We want to get rid of that even power and make it turn into something linear so that we can integrate it. So this is how we would apply that half angle identity. Now the identity for sine squared is exactly the same, it just has a minus inside, and notice it also changes to a cosine. No matter whether you're starting with sines or cosines, both of these turn into cosines. So how does this help me? Well, what I'm left with now is 1/2 times the integral of just 1 dx, or just dx, plus the integral of cosine 4x dx. And both of those are things I can integrate. The integral of dx is just an x. And the integral of cosine of 4x, we can do that because it's just a cosine, but be careful here. This is really cosine of u, where our u is this 4x. This is kind of like your inner function g, and the cosine is your outer function f prime. And in order to integrate this, I also have to have a g prime present. And the derivative of 4x is just a 4. So we're missing a 4 to have the right g prime, so I have to counterbalance by a 1/4. So that 1/4 is going to stay out front. I have all the 3 pieces that I need. The only piece of this that I integrate is the outer function, in other words, the cosine. So what's the integral of cosine? Sine. And it's going to be sine of this same g that we had originally. So that's what this turns into, 1/4 sine of 4x. Let me go ahead and distribute my 1/2 across. 1/2 x plus 1/8 sine of 4x. And there's no more integrals, so we can put on our plus c, and we have our antiderivative. So for even powers of sines and cosines, you're going to use those half angle identities. All right, the next example has odd powers again. So just like in the first example, when you have odd powers of sines or cosines, you're going to save one and convert the others. Now, which one should you save? It doesn't matter. You can save one of the sines and convert everything else to cosines, or you can save one of the cosines and convert everything else to sines. It's up to you. So let's just go ahead and save one of the sines. I'm just going to randomly pick. So what I'm going to do is I'm going to take this sine cubed, and I'm going to think of it as sine squared 2x, cosine cubed 2x, and then that extra sine of 2x, I'm going to push it off to the side. That's the one I'm going to save for later. So the rest of this I want to convert to cosines. If you're saving a sine, convert it to cosines, convert it to its opposite. So the sine squared, using that Pythagorean identity, is 1 minus cosine squared of 2x. You don't change the angle, you just do 1 minus cosine squared of the same angle. I'm going to leave this cosine cubed the way it is because it's already in terms of cosines, so I don't need to change it. But what I am going to do is distribute it across. So this becomes cosine cubed of 2x minus cosine to the 5th of 2x, and both of those are being multiplied by that sine of 2x that I saved dx. Now let's go ahead and break these two things up into two different integrals. And while I'm at it, I'm going to take that cube and I'm going to put it on the outside of my cosine function like that. So this will be cosine 2x quantity cubed times that sine of 2x dx. I'm really just distributing these across. Minus the integral of cosine 2x to the 5th times that sine of 2x that I saved. That sine of 2x that we saved is going to be part of that g prime, part of that u du. If you prefer to do a formal u substitution on these, that's perfectly okay. You would let your u be cosine 2x, then your du would need to be the derivative of that, which is going to be minus sine of 2x times 2, and then you can adjust from there. I personally find it's easier to think in terms of pattern recognition on these. It saves me some time from doing all of that u substitution stuff. So pattern recognition applied to this. The power is that outer function f prime. The inside stuff in the parentheses is your g. And the derivative of cosine 2x, use your chain rule on that, wants to be minus sine of 2x times 2. So I have everything that I need except the negative and the 2. So I counterbalance with a negative 1/2. And then I'll have the correct g prime. Out of all of these pieces, the only one you integrate is the power. So the integral of a cube is a 4th over 4. What's inside stays inside, and that negative 1/2 is still out front. Now I do that all over again on this one. The outer power is my f prime. The inner function is my g. The derivative of cosine 2x is a minus sine 2x times 2. So that would be my g prime. I need to counterbalance by a negative 1/2. So the minus minus becomes a plus 1/2, and the integral of something to the 5th is something to the 6th over 6, and the cosine 2x stays the same inside. And then just cleaning up my constants here, this becomes cosine to the 4th of 2x over negative 8 plus cosine to the 6th of 2x over 12 plus c. You could also write this as negative 1/8 cosine to the 4th of 2x plus 1/12 cosine to the 6th of 2x plus c. Both options are fine. Okay, so odd powers, save one, and convert the rest to the opposite function. Same thing that I'm going to do exactly right here. I've got a cosine raised to an odd power, a 5th power. So we're going to save one cosine, and we're going to convert the rest to sines. Okay? It's kind of messy handwriting there. Sorry about that. So I'm going to split this up. Now, to use those Pythagorean identities, they use squares, cosine squared plus sine squared. So I'm going to break this up into a cosine squared 4x times another cosine squared 4x times the one cosine that I'm going to save. So that's 2 plus 2 plus 1 is 5 total. I've got them all accounted for. This is the one I'm not going to touch. That's going to become part of my g prime later on when I do my pattern recognition. The other two I want to convert to sines. So I'm going to use Pythagorean identities for both of these and change them into a 1 minus sine squared for both. So this first one is 1 minus sine squared 4x times 1 minus sine squared 4x times that cosine of 4x dx. Now, unfortunately, you're going to have to FOIL all this out to get the correct trinomial that we need here. So 1 times 1 is 1. In the middle, I'm going to get a minus sine squared and another minus sine squared, so I'll get minus 2 sine squared 4x. And then I'll get a minus times a minus is a plus, sine to the 4th of 4x. Okay, now we're ready to split this up into 3 different integrals. So I'm just going to distribute these 3 things across. So I'll get 1 times cosine 4x dx. I'm going to go ahead and take this minus 2 and pull it out, and I'll get sine of 4x, and that one was squared, times our cosine 4x dx, plus the third one here is sine of 4x to the 4th times cosine of 4x dx. So I just made an integral for each of these three pieces with that cosine 4x on the side. Now we're ready to integrate. How do you integrate a cosine function? Well, it's going to turn into a sine function as long as you have the right du. This is your f prime. That's the outer function. So the 4x is your g. I need to have the derivative of that, which wants to be a 4, in here as well so that I have the right g prime. So I have to counterbalance by a 1/4. So the 1/4 stays put, and the integral of the outer cosine becomes a positive sine of that same 4x that I had originally. So this is just 1/4 sine of 4x. Same idea on this one, but now my outer function is the square. My g is sine of 4x. The derivative of sine is cosine, but the derivative of 4x wants to be a 4, so I need to be multiplying this by 4 as well to get all the right pieces for that g prime. So I have to counterbalance by a 1/4. 2 times a 4th is a minus a half, and when I integrate a square, it becomes a cube over 3, and what's inside stays the same. Okay, and then the last one, same idea. My outer function is the 4th. Here's my g prime. I'm missing a 4 in front here, so this will be 4 times cosine of 4x, counterbalanced by a 1/4. So the 1/4 stays there, and the integral of a 4th power is a 5th over 5. And then we're ready to put on our plus c. The last thing I'm going to do here is just combine some of those fractions. So I get 1/4 sine of 4x minus 1/6 sine cubed of 4x plus 1/20th sine to the 5th of 4x plus c. All right, let's try some tangents and secants this time. So now we have the integral of tangent to the 5th of x times secant of x dx. So the strategy here is if tangent is odd, you're going to save a secant x tan x, and then you're going to convert the others to secant x. The reason you want to do that is because if we can change these to powers of secant, then the derivative of secant would be a secant x tan x, and we're going to need that secant x tan x to be our g prime. So I'm going to split this up. I want to save one of the tangents along with the secant that I have to be part of my g prime. So we need a secant x tan x on the side, and we're not going to touch that. So if I pull one of those tangents away, that leaves me with a tangent to the 4th, which I'm going to change to a tangent squared times a tangent squared. And then I'm going to use my Pythagorean identity for tangents and convert both of these into secant squareds. So the identity is tangent squared x is equal to secant squared x minus 1. So I'm going to use that twice, here and here. So this becomes secant squared x minus 1 times secant squared x minus 1 times that secant x tan x dx. Now, just like in the last problem, you're going to want to FOIL this out, and you're going to get powers of secants. So this is going to be secant to the 4th x. You'll get a minus secant squared and another minus secant squared in the middle, so that'll be minus 2 secant squared x, and then a plus 1. And then if you need to, you can integrate directly from here if you can visualize it, or if you want, you can break this up into 3 different integrals, each one having that secant x tan x on the side. So this first one will be secant x to the 4th times that secant x tan x on the side, minus 2 times secant x squared times that secant x tan x on the side, plus the last one just has the secant x tan x by itself. So if we look at this first one, pattern recognition, the power is our f prime, the inside function is our g, the derivative of secant x is secant x tan x, which is exactly what we saved, so we don't even need to counterbalance anything. We're ready to just integrate that 4th power. So it becomes a 5th power over 5, and what's inside stays put. For this one, same idea. Here's your f prime, here's your g, and all of this is your g prime. So when I integrate a square, it becomes a cubed over 3 times that minus 2 that was already out front. And then the last one doesn't have any function in front. So this is just asking, well, what function has as its derivative secant x tan x? Or what's the antiderivative of secant x tan x? That's just a plain old secant x, because the derivative of secant is secant tan. We're all done. Just put a plus c on it, and there's our final answer. So that was when we had odd powers of tangent. You save one, and you convert the others to secants. So now what do you do if you have even powers? Well, if you have an even power of secant, you're going to save a secant squared, because that is the derivative of your tangent. So we're going to think of that secant squared as our g prime. So I'm going to save a secant squared, and that means I still have another secant squared left since I had 4 of them, and I'm going to leave the tangents the way they are, because what I want to do here is keep this one off to the side as my g prime, and that secant squared is the derivative of tangents. So I want all of this stuff to be tangents. This one already is, so this is the only one I have to change, and I'm going to use that Pythagorean identity to do it. This one becomes tan squared of 2x plus 1, since tan squared plus 1 is secant squared. The tangent raised to the 6th of 2x, you're going to leave the way it is because it's already in terms of tangents. And the secant squared x is what we're saving off to the side. So this, remember, is your derivative of tangent, so that's why we want all this other stuff in terms of tangents. If I distribute, I'm going to get tangent to the 8th of 2x plus tangent to the 6th of 2x times secant squared x dx. Oops, I lost a 2 there, sorry. And now I'm going to break this up into 2 different integrals, this one and this one. So we'll get tangent of 2x to the 8th times that secant squared 2x plus tangent of 2x to the 6th times secant squared 2x dx. So the reason why this strategy works is because of pattern recognition. There's your power, here's your g. The derivative of tangent is secant squared. Derivative of 2x is a 2. So I've got the secant squared 2x. What I'm missing is a 2 as well. So you put in a 2, counterbalance by a half, and you integrate an 8th power into a 9th over 9 times that 1/2, and what's inside stays put. Then we do it again over here. Here's your outer power, here's your g. The derivative of tangent 2x is secant squared 2x times 2. So we're missing a 2, put it in, counterbalance. And the integral of a 6th power is a 7th over 7. The 1/2 stays out front, and the tangent 2x stays the same inside. And then just cleaning up our fractions here, this is a 1/18th tangent to the 9th of 2x plus 1/14th tangent to the 7th of 2x plus c. Okay, integral of sine squared x dx. So this should be a refresher of something we've done before. If you have an even power for sines or cosines, then you're going to use those half angle identities. So the half angle for sine squared is 1/2 parentheses 1 minus cosine of the double angle 2x. So we're still converting it to cosines, whether it's a sine squared or a cosine squared. But for the sine formula, you use a minus. For the cosine squared formula, you use a plus. That's the only difference. So this is going to become 1/2 times 1 minus cosine of, the original angle here is x, so when I double it, it becomes a 2x. And then I can split this up into two separate integrals. The integral of 1 dx, or just dx, minus the integral of cosine 2x dx. The integral of dx is just x minus, to integrate cosine 2x, you have to think in terms of pattern recognition here. The cosine is your f prime, the 2x is your g, so you have to have g prime in here as well. And the derivative of 2x is a 2. So you're missing a 2 to make this work. So you counterbalance by a 1/2. Now you have the right three pieces. That minus 1/2 stays out front, and the integral of cosine is sine. You don't need to change the positive or the negative out front. It's going to just stay sine of that same 2x that you started with. If I distribute my 1/2 across, I get 1/2 x minus 1/4 sine of 2x, and then a plus c. So even powers of sines or cosines use that half angle identity. How about odd powers of tangent? Well, we know that the derivative of tangent is secant squared. So this doesn't have any secants that we can use to save on the side for our powers of tangent. We would need to have a secant squared dx available in order to have the correct g prime. And we don't have that here. So what we're going to do is we're going to convert our tangents into secant squareds. So we're going to break up this tangent cubed into a tangent squared times a tangent. And the tangent squared is going to become a secant squared x minus 1 using that Pythagorean identity. And then I'm just going to distribute these across and break it up into two integrals. So I'll get secant squared x times tangent of x dx minus 1 times tangent of x dx. Now I'm going to rewrite this just a little bit so it's a little easier to see. This is like tangent of x times secant squared x dx. I didn't really do anything but switch the order around. But if it makes it more obvious, I'm going to raise this tangent of x to the first power, because this is pattern recognition, where that first power is your outer function f prime, your g is the tangent, and the derivative of tangent is secant squared, so that makes this your g prime. So this does have all the right pieces. That's why we wanted that secant squared in there, so that we could use it as the derivative of our tangent. So we integrate only the outer function, and the integral of something to the first becomes something to the second over 2. We didn't have to counterbalance by anything, so this is just tangent squared over 2. Now when you get to this one, you can't do that because you don't have that secant squared in there. Now this is a formula we have talked about in the past, and either you have it memorized or you're going to have to rederive it. So just to kind of refresh your memory, to do this one, we're going to actually change tangent into sine x over cosine x. And notice that the derivative of cosine is minus sine, which I almost have. I'm just missing the minus. So I put it in and I counterbalance by a negative, which makes that a plus. And by doing that, this becomes stuff prime on top over stuff. So this is the integral of stuff prime over stuff, which is an ln of the denominator. So if you have a cosine in the bottom and its derivative on the top, then this is going to become the ln of that denominator, or the ln of cosine of x in absolute value. So that's a formula that we've memorized in the past. Negative ln cosine of x is the integral of tangent of x. We had a minus already, so that's why it turned into a plus. This is also known as the ln of secant of x if you don't have that negative in front. Put a plus c on the end, and we're done. Now the next example is a little different looking because we've got the integral of sine 3x cosine 4x dx. We don't have any powers here, so we're not going to save any sines or cosines or use any Pythagorean identities or half-angle identities, but we are going to use an identity, and it's not usually one of the ones we have memorized, so I would allow you to look this up. The reason we have to do something special here is because the two angles, this 3x and this 4x, are different, which makes this difficult to do. So what we're going to do whenever those two angles are different is use a product to sum identity, which is something that looks like sine u times cosine of v, like this one. We have a sine times a cosine where the u and the v angles are different. Sometimes you might see a sine of u, sine of v, or a cosine u, cosine of v, and there's equivalent formulas for those that you can look up in your book in the back or the front cover. So this one has the form of sine of u times cosine of v. So the product to sum identity that applies for that case is 1/2 sine of the u minus v plus sine of the u plus v. So let's apply that to this. So this is going to be 1/2 parentheses sine of, this is my u and this is my v. So we want the u minus the v, so 3x minus the 4x, plus sine of u plus v, so 3x plus 4x dx. Now simplify that before you go on. Let's go ahead and pull our 1/2 out, and this becomes sine of 3x minus 4x is a negative x, and 3x plus 4x is 7x. Now one more thing we're going to use here. Remember that sine is an odd function, which means any negative inside of that argument can be pulled out, and this becomes a minus sine of x. So I'm going to go ahead and I'm going to pull out that minus sign. So now we're ready to integrate. If you need to, you can break this up into two integrals. It's up to you. This is going to be negative times the integral of sine x dx. I pulled that minus all the way out of the integral, plus the integral of sine of 7x dx. So we get 1/2 times bracket negative. The integral of sine is negative cosine. So these minuses are going to cancel out and make this become just a plus cosine. Then for this one, be careful, because you don't just have a sine of x, you have a sine of 7x. So your outer function is the sine, your g, or your inner function, is the 7x. You can't integrate this unless you also have g prime present, which wants to be a 7. So we're missing a 7 to have the right g prime. I have to counterbalance by a 1/7. So this becomes 1/7 times the integral of sine is negative cosine of that same 7x that we started with. So just distributing my 1/2 across, we get 1/2 cosine x minus 1/14 cosine of 7x, and then we have our plus c on the side, and we're done. All right, our last example here, we've got sine squared x cosine squared x dx. Now this one has both of them being even powers. If we had one of these being odd, then we could save one of those, one of the odd ones, and convert the others to the opposite function and be able to sort of do our pattern recognition on it. But if they're both even like this, then we're going to use those half angle identities. So if they're both even, we're going to use that half angle identity. And remember, that's the one that doubles the angle. So the half angle identity for sine squared x is 1/2 1 minus cosine of the double of this angle. So that's just going to be 2x. For cosine squared, it's also 1/2, but it's 1 plus cosine of 2x dx. Now this 1/2 times this 1/2 is a 1/4, so let's pull that out. And that means we're left with a 1 minus cosine 2x times 1 plus cosine 2x. We are going to need to FOIL that out. So let's do that. It's actually a difference of squares. So, whoops, that means our middle terms are going to cancel out. So we're just going to get a 1 times 1. The inners and the outers cancel, and then we'll get a minus cosine 2x times a plus cosine 2x, which is a minus cosine squared 2x. So if we break this up into two integrals, we're going to get 1/4 times the integral of just 1 dx, or just dx, minus the integral of cosine squared of 2x dx. Now the integral of dx is just x, but the integral of cosine squared 2x, we don't know what that is, because if you change that to a cosine 2x quantity squared, you can't do pattern recognition on that unless you have the derivative of cosine 2x present, which would mean we would need to have a sine of 2x in this integral as well, which we don't have. So this doesn't have a direct antiderivative, but look at the power, it's even. If you have even powers on sines or cosines, then you can use your half angle identity. So we're going to use our half angle identity again, a second time. So this is going to become 1/2 1 plus, because it's a cosine of the double of this angle. So when I double 2x, it turns into a 4x. Each time you use your double angle identity, you're reducing this power down, which is good for us because we're making the inside function get simpler. We're losing that power, so instead of being a square, now it's linear. So let's see what we have. We've got that 1/4 way out front, and we have our x. I'm going to take this 1/2 and I'm going to pull it out, and we're going to get 1 plus cosine of 4x dx. And you can integrate right away here. I'm going to just be super careful and try to break everything down as much as possible. I'm going to break this and this into two separate integrals. Each one is going to get that minus 1/2 in front. So we'll have a minus 1/2 times the integral of 1 dx, and then we'll get a minus 1/2 times the integral of cosine of 4x dx. We still need to integrate each of those. So the integral of 1/2 dx is just 1/2 x. The integral of 1/2 cosine of 4x, this is that pattern recognition. The cosine is your outer function. The 4x is our g. The derivative of 4x is a 4, so I need to have a 4 in here to have the right g prime. So I need to counterbalance by a 1/4. So we're going to get a 1/8 out front, and we integrate just this outer function, which is that cosine. The integral of cosine is sine, and it's going to be sine of 4x. So last but not least, let's kind of clean some things up here. X minus 1/2 x, this is like 2/2 x minus 1/2 x is going to be 1/2 x. So if I clean those like terms up, then these two turn into just that single term, and 1/4 times 1/2 x is going to be a 1/8 x, minus 1/4 times 1/8 is 1/32 sine of 4x, and I have my plus c on the end. And that's it. Alright, so even powers of sines and cosines, typically you're going to use those half angle identities. If you have an odd sine or cosine, then typically you'll save one of them, one of those odd ones, and convert the others to the opposite function. For tangents and secants, then typically you're going to want to save either a secant squared x if you have enough secants available to do that, or you're going to save a secant x tan x if you have enough of those available, and use those Pythagorean identities. Alright, that concludes our video lecture on powers of trig functions. Good luck!